Well, it's my pleasure to introduce Valerio Laredo for our third and final talk of the day from Northeastern University, who will be speaking about Stokes phenomena, Poisson-Lie groups, and quantum groups.
Okay. Thanks a lot, and thank you very much to the organizers for inviting me to give this talk. So my setup is going to be the following. I'm going to start with a complex semi-simple group, connected and simply connected. And the starting point is going to be two well-known, or maybe very well-known stories. One having to do with the quantum group corresponding to G, and specifically its construction from the Kazhdan homological equations. This is a story that started with Drinfeld and was later developed by Kazhdan-Lusztig and Kazhdan. And then the other story has to do with the semi-classical limit of the quantum group, so the dual Poisson-Lie group, G star, and specifically the fact that you can get its Poisson structure from Stokes phenomena with values in G. This is something that was discovered by Boalch in the early 2000s. So my goal so what I'd like to explain today, I mean, after reviewing these two stories, is first of all to give a slightly different but construction of the quantum group, but entirely transcendental. So I will start from the KZ equations, but sort of take the KZ equations all the way through, so to speak. And then I will also show that Boalch's construction, which kind of has a similar flavor in the sense that to the construction of UQG, in the sense that it uses differential equations, but that similarity to date was more like a sort of heuristic and rather vague. But I will explain that there's a theorem that you can prove, and this theorem is joined with Xiaomeng Xu, and the theorem that I'll state and sketch is that the Boalch's construction of this Poisson structure is actually the semi-classical limit of the transcendental construction of the quantum group that I will present. Okay, so and maybe before I get started, I should make a kind of a word of apology. Everything I'm going to say is going to be extremely unmodular. So you already see from my notation I'm using UH bar of G. So I'll think of the quantum group as defined over the ring of formal power series. That's kind of for maybe for convenience. It makes some of the statements I'll state a little easier to formulate. H bar can be specialized to a numerical value, but not to a rational value, at least not presently. So again, I will stay very well away from roots of unity. All right. So let me briefly remind you then how you go from the KZ equations to the quantum group. So the KZ equations are the following: we take n, we fix an integer n, we take n representations of G, and the KZ equations are a system of differential equations for a function with on Cn, so a function of n variables with values in this n-fold tensor product here. And specifically, they're the following partial differential equations. So df over dzi is the sum over j not equal to I of omega ej zi minus zj. So it's the linear equation, and this omega ej, which is defined here, is a Casimir for G. So there's a sum over a basis and a dual basis with respect to a fixed invariant bilinear form, and it's a kind of Casimir operator, but it on two different legs. So it has a leg on the ith tensor component and a leg on the jth tensor component. And then it's a well-known fact that these are integrable partial differential equations, so they form a flat connection, and moreover they're equivariant under the obvious action of the symmetric group. And so they define under monodromy a representation of the fundamental group of this quotient space, which is the finite break group on n strings, to a representation of this break group acting on this n-fold tensor product. Okay, so now how does the quantum group appear? Well, the first idea goes back to Drinfeld, and it is that the monodromy of these KZ equations. So if I tower up all these KZ equations for all n's, and then these form they can be sort of consistently put together, and they give the structure of these representations the structure of a braided tensor category. So specifically, the commutativity constraint is, so that's the thing you would associate to such a diagram. That's just the permutation of the two tensor copies preceded by the Casimir, or the exponential of the Casimir on just two tensor copies. That's the commutativity constraint. And the associativity constraint is something that's called phi KZ. And this is something that you can extract from the KZ equation in 3 points. And it's a holonomy between two canonical base points. And the first base point having to do with this bracketing here is a base point that you can think of as being associated to the regime where Z1 and Z2 are much closer together than Z1 and Z3. So you should think of V1 over Z1, V2 as living over Z2, and V3 as living over Z3. And the second bracketing is associated to the regime where Z2 minus Z3 is much smaller than Z1 minus Z3. Okay. So this is the first step, and having established that, which in kind of Pullman's language means that these two ingredients determine all the tower of these representations, and then these two ingredients satisfy a bunch of identity, hexagon and pentagon. So having observed that, Drinfeld shows that this category of representations is equivalent to the category of representations of the quantum group, again in the formal setting, with its Drinfeld-Jimbo R matrix and trivial associator. So here we have a strict category. And the fact that this is so, at least in Drinfeld's proof, follows, by the time you've made this observation, by cohomological rigidity. So basically, he proves that there's no other solutions to these hexagon and pentagon equations. And so this is good and short, but of course, the weakness is that you cannot specialize it in any value of H bar. Now then, the second idea is due to Kazhdan and Lusztig and is based on the Tanakian formalism. And it stems from the fact that if you believe that such an equivalence should hold, then what we'll usually call the Drinfeld category, so the representation of the quantum group with this monodromy data, then is endowed with a fiber functor, with an obvious fiber functor, because this one here is, and moreover, the quantum group is the Hopf algebra of endomorphisms of this fiber functor. So then, what Kazhdan-Lusztig suggests is, what about if we try to construct a different and perhaps canonical and better fiber functor here from this very same Drinfeld category to vector spaces over H bar, and then show that the quantum group arises as the endomorphisms of this fiber functor. And that's what they set out to do, and that's what they do. And for I just say a word about the details, though they won't be relevant for what I'll say next. But what they do is they represent, as a functor of abelian categories, they represent this functor to be by the object UG. And then, and this is where the work comes in, they essentially prove that the UG in this Drinfeld category here has a natural coalgebra structure for which it is polarized. So there's a kind of PBW polarization of this object as coalgebras, as the tensor product of the negative Borel and the positive Borel. And a corollary of their construction, because everything is canonical and defined by formulas, is in particular that you can specialize things to, at least immediately specialize things to non-rational values of the deformation parameter. And then with more work, you can also get to root unity. And so so that was for Kazhdan and Lusztig. And now the third and final idea in the story is due to Ettinghoff and Kazhdan. And so they noticed that the Kazhdan, or proved that the Kazhdan-Lusztig construction can be vastly generalized. So G need not be semi-simple for that to work. All it has to be is the Drinfeld double of a Lie algebra, and in fact of a Lie algebra over a field of an arbitrary an arbitrary field of characteristic 0. And to do that, you can replace the KZ associator if your field is not the complex numbers by any so-called Lie associator. So that's a formal power series in two non-commuting variables A and B that satisfies the pentagon and hexagon equations that I mentioned. And as a corollary of their generalized construction, you can quantize any Drinfeld domain, in fact, any Lie algebra over such a field. And this is good for outside of Kac-Moody, because outside of Kac-Moody there was no independent construction of the quantum group, and so Etinghoff and Kazhdan give you a functorial such construction. Okay. So this was to review this appearance of the quantum group from differential equation. Now let me explain this transcendental construction of UQG. So now UH bar of G. Now I want to specialize back to the field of complex numbers and to a semi-simple algebra, and I want to replace the Kazhdan-Lusztig functor by a, so to speak, purely transcendental functor. And of course, you may ask, given the generalization of what the generality of what I just explained, why you'd want to do that. So there's a small stylistic reason, which is that if you've seen the Kazhdan-Lusztig construction, you start with something that comes from differential equations. This is this braided tensor category here. So it's transcendental. And then you kind of, so to speak, throw away analysis and you just replace this by algebraic manipulations and prove factorizations like that. So what I'd like to do is something that is transcendental all the way. So that's a kind of small cosmetic or stylistic reason. That the more serious reason is that this construction, which I will sketch, is a key ingredient in the proof that the monodromy of another differential equation associated with G, namely the Casimir equation, which gives representation of the braid group of G. So not the Bn, but the Coxeter braid group. So that the monodromy of this Casimir equation is given by Lustig's quantum Wahl group operators for the quantum group. And for that, you need a fiber functor, which you need to sort of pick a good fiber functor. And I don't know how to make these this Casimir connection appear out of, for example, the Kazhdan-Lusztig functor. So that's why it was kind of forced to find this construction. So the main ingredient is going to be still the KZ equation. So we're going to stay within a kind of pretty confined domain. However, with a little twist, namely, they're going to be the dynamical KZ equations. And so the dynamical KZ equations, so I'm writing here for you what they are in 2 points. So we're going to fix n is equal to 2. That will be sufficient for what we need. So we have two variables, Z1 and Z2. Z will be their difference. And so if I were to delete this term, oops, I actually did delete it. That's not what I wanted to do. Okay, so what I was about to say was if I were to virtually delete this term here, then I would have the KZ equations on 2 points, which are the ones from which the commutativity constraint arise. But nothing much more can arise from that. They have this essentially a Z-fold of monodromy. That's it. So now we're going to put this interesting twist. We're going to put mu here. And what is mu? Mu is a fixed element in the Cartan subalgebra. And of course, if mu is equal to 0, you recover on the nose the KZ equations. Mu1 means that simply mu is acting on the first tensor copy, or the first representation only. Okay, so now that we have this equation, let's talk about its two. So this has two singular points, 0 and infinity, as did the undynamical KZ equation. So let's look at them a little bit more closely. So for Z is equal to 0, we have a regular singularity, as we did in the undynamical case. And it followed pretty easily that there is a unique fundamental solution of the following form. So its singular behavior is Z to the H bar omega. So that's this term here. Okay, and then it has a holomorphic part. So it has a holomorphic function on C with values in the second tensor power of UG, and uniquely normalized by the fact that at 0 it takes a value 1. So this is the solution in which the monodromy of the standard loop around 0 is on the nose this operator here that I introduced earlier here. So that's this is the same analysis you would do in the undynamical case. Now for the let me put the whole slide. So for the singularity at infinity, we meet something new, and that's the price we pay for having introduced that new. Namely, we have an irregular singularity. And so you can see that by changing variables, you put zeta is equal to 1 over z, and then the equation becomes that, and you see that this mu of 1 has a coefficient of 1 over zeta squared. So this is a pole of order 2, which is the kind of the simplest non-trivial irregular singularity you can have. So now to say something about solutions of this differential equation near z is equal to infinity. Roman is asking me what is dynamical about and why the name. I'm not sure, actually. I'm not sure about, well, dynamical in the sense, yeah, I'm not sure why the in this general business, it's standard to have this sort of dual parameter, dual Kazhdan parameter. Why call it dynamical? I don't know. It's because it's a dynamical variable, because maybe because there's a differential equation that appears with respect to it as well, as I'll say in a minute. And in some other contexts, there's a difference equation that appears with respect to this parameter. So yeah, so I was going to say something about so solutions of this differential equation near this irregular singularity. So I'm going to first make a pretty standard assumption, which is needed for the form of the solutions I'll give, which is that my mu is an irregular element in the Kazhdan. So this is an assumption you would make even for differential equations with values in a finite dimensional vector space. And then it follows fairly easily that there is a unique solution here, unique canonical solution, which the singular behavior of it is now e to the z mu1, as you would expect from the differential equation, times z to the h bar, here, h bar omega 0. So that's omega 0 is not omega anymore, but it's the Kazhdan part of omega, and so which is actually the part of omega that's centralized by the singular term here, mu1. And then there's a kind of, so to speak, wannabe holomorphic function. So to speak specifically, there's some function which is valued in second power of UG, but it's a formal function of Z inverse, normalized by the fact that at infinity, it takes the value 1. Now, because this is an irregular singularity, you meet a rather standard problem in this story, which is that the radius of convergence of this wannabe holomorphic function is actually 0. So this is a function which is formal and is not holomorphic in any reasonable sense. And the solution of this, at least if your ODE were to take values in a finite dimensional vector space, which is not the case for us, we're taking values in the second tensor power, would be to take this formal function and resum it. So do some kind of Borel sum of some appropriate transcendental procedure, which would turn it into a holomorphic function. And this holomorphic function would be holomorphic in half planes. So something like you take a fixed direction in the complex plane, and then you multiply. You go pi over 2 clockwise, pi over 2 anti-clockwise, and this is your typical half plane. And in the finite dimensional setting, this can be done for all but finitely many values of the dissecting direction of the half planes, and these finitely many values are called Stokes directions. So again, in finite dimensional coefficients, this is a well-known story. Now, if you try to copy the story in with values in this infinite dimensional vector space or algebra, then there can be infinitely and in fact densely many Stokes rays, and so that makes your story pretty complicated. So you can't invoke a sort of a standard OD textbook result. And so to proceed, I'm going to make a further assumption which you would not make in the finite dimensional setting, which is that mu is actually a real element in the Kazhdan. And that kind of collapses all these Stokes directions. That's why I make this assumption. It collapses all the Stokes direction onto the real line. So now, even though there could be many Stokes rays, they're all collapsed. And so there's only two problematic directions, which are positive real axis, negative real axis, and all the others are good. You still can't in the text, at least you're in a situation where you might. And indeed, the result is the following.
You're muted.
You're muted, Valerio.
Okay. And can you see my screen?
Nope.
My iPad? No, you can't.
No.
Okay, so I guess I have to. Hold on. Okay, you can now, right?
You sort of froze when you were at the end of the last page.
Oh, I see. So it's been a while. I see.
Okay.
So do I assume that you heard everything that's said on this, that's written on this page?
You said that the Stokes directions were on the real axis, and you were starting to say something after that and broke up.
Okay, so then I said, so that collapses the Stokes direction, so that removes the problem of infinitely and densely many Stokes rays. You still can't invoke an OD textbook, but at least you hope that you might be able to prove something like you would find in a textbook. And this is the next theorem. So now hopefully the connection is not going to jump. So that's what happened, I guess, when you deal with irregular singularities, that your iPad doesn't like it. So there's two canonical fundamental solutions, which are holomorphic, and they have the desired asymptotic behavior, singular behavior near z is equal to infinity, so e to the z mu1, z to the h bar omega 0. But then you have to tend to z to infinity either in the upper half plane or in the lower half plane. Okay, so that's the first thing. So this is like, this is sort of complementing kind of an OD textbook kind of result. And now you can take the following. So now we have at 0, we have this fundamental solution psi 0, and at infinity we have these two. So pick one, and then form their multiplicative difference. So this is a kind of regularized holonomy from 0 to infinity, either at I infinity or negative I infinity. And the claim is this is a tensor structure on the forgetful functor from this Drinfeld category to vector spaces over H bar. So what that means is that, it just means that this diagram is commutative. So I can take 3 representations and I can forget them with brackets. Of course, because vector spaces, it doesn't matter where I put the brackets at this level here, right? But if I look at them like this, I can apply this tensor structure that I introduced, and I use that to identify with that. And then I can use again the tensor structure and identify with this. Or I could do the same with a different system of bracketings here and get here. And now I have a preferred way to relate this and that, which is the KZ associator. And the claim simply means that this diagram here is commutative. Okay, so this regularized parallel transport from 0 to plus or minus I infinity, which I got from the irregular singularity at infinity, actually kills the KZ associator in a completely sort of transcendental way, so to speak. So I never have to invoke any kind of categorical yoga to do that. And the bonus that I get from this, and that's, as I mentioned, that's the reason I had to do this construction, is that this J, which of course depends upon my parameter mu, because mu was put in right from the start, varies well when I vary mu. So it specifically satisfies a differential equation or a flat connection with respect to mu. And this flat connection is, for those of you who know it, is the Casimir equation acting on the left diagonally and on the right as a kind of on one copy or the other. So it's a sum. So it's a differential equation on the regular Cartan, and it says you take the sum over all positive roots, the logarithmic derivative of the root, and then you have the Casimir. C alpha is the Casimir operator for the copy of SL plus, which sits inside G. And then it's acting on the left as diagonal and on the right as one tensor copy or on the other. Okay. So now let me make a few remarks. The first I've already made. So the first part of the statement, namely the existence of these solutions, is in form at least, is a standard textbook type of result, but we do a little analysis to prove it in this infinite dimensional context. The second is maybe this heuristic interpretation, maybe why you'd want to call it a fusion operator. It's something that, as I mentioned, relates a solution, the fiber of this flat connection, where the 2 points are infinitely far apart. So you can imagine that the representations as not talking to each other, they're kind of very, very far away. And then you relate it in a regularized way to what happens when both representations are sitting above the same point. So it's a kind of way to fuse these representations. And then third, the interpretation of this differential equation is the following. You could object that now in the Kazhdan-Lusztig setting, for example, there was a preferred canonic of a fiber functor. Now I have a huge family of fiber functors varying with mu. But this one way to look at this differential equation is to say that as mu varies, then this tensor structure on the fiber functor only varies up to infinitesimal gauge transformations or natural transformations. So in other words, up to natural transformations, there's really I'm only producing one tensor functor. Okay. All right, and then the next result, which you would expect, is that the endomorphisms of this fiber functor here is given by the quantum group, and you can prove this in two ways. So the first is a kind of cheap but quick proof, and you can use Drinfeld's uniqueness. And Drinfeld's uniqueness says that the quantum group is the unique quantization of G that's equivariant for the Chevalier evolution, and you can check that that's true. But maybe that's not a very good proof. I mean, in the sense that, for example, it doesn't allow you to specialize. And a better proof that I'm currently working out with Andrea Appel is that you can actually realize this isomorphism explicitly. So you can actually, it seems like we can actually give some fairly natural endomorphisms of this fiber functor, which satisfy the quantum set relations and defining relations of the quantum. Okay. Another remark is this fusion operator construction can be generalized to a symmetrizable Kac-Moody algebra. So I've done this in a paper with Andrea from a few years ago, actually. So everything generalizes to a symmetrizable Kac-Moody algebra, and needed for the same reason to make this Casimir connection appear and Lustig's quantum Wahl group appear. And finally, let me say that this fusion operator could potentially have some interesting number theoretic aspects to it, and specifically, it's well known that the KZ associator is the generating function, generating series of multi zeta values. And now the fact that we can kill it with this fusion operator, which is to say that this identity holds, should mean that these multi-zeta values are expressed in terms of other periods, namely the periods that you get when you try to explicitly work out this fusion operator. And these are not periods in the canonical sense. They appear to be exponential periods. So Rafael is asking me whether I construct the quantum group as a sheaf of the hyperplane complement. So yes and no. So no, in the sense that as an algebra, it's completely independent of. So you can, it's kind of a trivial sheaf as an algebra. It's always the same thing. It's always the endomorphisms of this fiber functor. The coproduct, of course, then does depend on mu, because the coproduct is the twist of the standard coproduct on the developing algebra by this fusion operator that I introduced. So that does vary interestingly and according to the Casimir equations over H reg. So that's the yes part to Rafael's question. Okay, all right. So I'm about to switch gears and talk about Boalch's constructions, but maybe I can ask if there's any questions so far. Okay, I think there's a silent no. So let me review then Boalch's construction. So Boalch starts from a differential equation of a type that we just looked at. So it's the f over dz b over z plus a. So what b is a general element in my semi-simple Lie algebra. G and h is an element in the regular Kazhdan. As I mentioned, this is a standard assumption. And I'm now going to make a non-standard assumption, and one that certainly Boalch does not make, which is that this element is real. And again, here it's totally unnecessary. It will just make stating what I'm about to state a little simpler. So just a convenience assumption here. Now, as before, we find that Z at infinity, the Z is equal to infinity is an irregular singularity. And so by the textbook analysis, there are two canonical fundamental solutions which are holomorphic in the upper and lower half plane. I'm calling them phi plus or minus, and they have the corresponding singular behaviors as Z tends to infinity. So Ez to the A, Z to the B in brackets, and B brackets means the projection of B onto the Kazhdan, so the diagonal part of B. And more generally, you'd have to project B onto the centralizer of A, but I've assumed A is regular. So, okay. And now I'm going to tell you a little, I'm going to do a little analysis, which I didn't explain before, which is we're going to now look, earlier I was going from 0 to infinity. Now I'm going to stay just at infinity and tell you a little local story. So at infinity, I have these two solutions. So I have phi plus defined in the upper half plane and phi minus defined in the lower half plane. And I'm going to want to continue these analytically continue these solutions. So if I take phi plus and I continue it like this in the lower half plane, then I'm going to find phi minus times a constant element of G. And I'm denoting this constant element S plus. And I can do a similar thing with S minus. I'm going to F phi minus. I can start here and then I can analytically continue it above in the upper half plane, and ignore this factor for now. You'd think that you should just get phi plus times a constant factor, and that is correct. But I also want to account for the fact that in going from the lower half plane to the upper half plane, we've crossed a log cut, and so we caught a factor of e to the 2 pi I diagonal part of B, which is here, right? And so I want to account for that. And so I'm normalizing my constant. I'm writing my constant as a part of an S minus and this phase factor here. And now you can think of this S plus and S minus as kind of half monodromies, in the sense that if I were to do, what we like to do, which is to take the full loop around infinity, say express the monodromy of this full loop in the fundamental solution of phi plus. If I do it in stages, so go from top to bottom, then bottom to top, then of course I would find this product here. So I would have this neat factorization of the monodromy in a kind of Gauss or LU decomposed form. And the other fact is that these once you normalize them like this, these so-called Stokes matrices or Stokes multipliers are actually unipotent. And unipotent in the sense that you remember that my diagonal term was regular. I also assume that it's real, so it lies in a certain chamber. To that chamber, I can associate a triangular decomposition. And then it's a standard OD fact that these multipliers, one lives in the upper unipotent group corresponding to the chamber, and the other one corresponding to is in the lower unipotent group corresponding to that chamber. Okay. Okay. And it's also a well-known fact from ODE theory that these are actually the right invariants to take if you want to capture the gauge equivalence class of the differential equation. So you could be tempted to say, why don't I just remember the monodromy? But that would not remember the whole differential equation. Could be inequivalent differential equations that have the same monodromy. On the other hand, if you take care of these, if you remember these Stokes factors and this local abelian monodromy, then that captures completely the gauge equivalence class of the differential equation. So that's why these are the right things to take. And now this is a theorem this is a beautiful theorem that Boalch proved. He said, let's consider the so-called Stokes map. So this is a map that goes from Gothic G star to the Poisson-Lie group. So as a source, I'm going to take B. So I'm going to look at my B, remember here, as a parameter of my differential equation. It was fixed, but I can think of it as as varying in the Lie algebra. So I'm going to think of it as a parameter, and I'm going to associate to it essentially it's the Stokes data. So essentially, because I'm taking S minus, but I'm multiplying it by the square root of that abelian monodromy at infinity, and then instead of taking S plus, I'm taking its inverse, and then again I'm multiplying by the square root of that abelian monodromy. And so now I'm getting two elements, one in the positive Borel, the other one in the negative Borel, which coincide over the torus. And this, by definition, and as a group anyway, is the Poisson-Lie group corresponding to G. And then Boalch proves that this map now, if I identify G with G star using the killing form, then this map becomes a Poisson map. And moreover, it's a local analytic diffeomorphism at least if I change the topology on this Poisson-Lie group, like I kind of force it to become simply connected by replacing the torus by its Lie algebra. But maybe we don't want to worry about this detail. So essentially, this is a local analytic diffeomorphism, which is a Poisson map. And this is a remarkable result because the Poisson structure on G star is the standard Poisson structure is a constant Poisson structure, and the Poisson structure on this is I mean, it's not very complicated, but it's certainly not constant. So you can think of this as a linearization result for the Poisson-Lie group G star. And there's a long story of such results. This was proved by Ginzburg and Weinstein in '92, but by kind of cohomological methods, so not constructively. Then after Boalch's work, Alexeyev and Meinring reproved it concretely using for the unitary groups. And then there was a formal proof by Enriquez, Tinhoff, and Marshall in '05, which is pretty general. So anyway, there's been a bunch of these results, but the flavor is always the same, that this Poisson-Lie group with a complicated Poisson structure can be linearized, so made isomorphic in maybe the formal category in this case, or in an analytic category in this case, to its Lie algebra in such a way that the Poisson structure becomes exactly the KKS Poisson structure. Okay. All right, so this was Boalch's construction. And as I said, this is a kind of similar flavor to what I explained before. You're using differential equations to find now the semi-classical version of the quantum group. And now what I want to relate those two, and to do that, I need to maybe remind you briefly of one ingredient, which is how you actually take semi-classical limits. So let me review the so-called quantum duality principle, which is due to Drinfeld and Gavarini. And so this principle states that the quantum group has two specializations. One is the obvious one. You set the parameter to 0 and you get the enveloping algebra. And the other one is you set the parameter to 0, but before you have to do a little preparatory work, which I'll remind you of in a second. And in that case, you get a different Hopf algebra, which is now commutative, but not co-commutative, and is the algebra of functions on the dual Poisson-Lie group corresponding to G, or better said, it's the formal quantum group, the completion at the identity. So what is this? So let me remind you the framework a little bit. So let's take a QUE in general, so quantized universal enveloping algebra. So that's a topological Hopf algebra, also over the string of formal power series, such that when you specialize it, you get an enveloping algebra. So for example, we could take the quantum group. Then we can define a Poisson cobracket, which is a map from UG to its second tensor power, and I do that by taking an element. I take a lift of it in this QUE. Then I take its quantum coproduct. I subtract the quantum coproduct, but with the two legs flipped. And then now this is something that's divisible by h bar, because at h bar is equal to 0, I have something that's co-commutative. So then I divide by h bar, and now I evaluate at h bar is equal to 0. And so that's a well-defined map from UG to UG tensor 2. And it specializes to a map from the Lie algebra to its second exterior power. And then you can prove that G with its original bracket and this co-bracket that we just introduced is a Lie bialgebra. And the good thing about Lie bialgebra is you can dualize them. So you can take the dual space, and now I can take the dual co-bracket that's now a bracket, and the dual bracket here that's now a co-bracket, and this is also Lie bialgebra. And if I think of it as a Lie algebra, then it has an underlying formal Poisson-Lie group, which I'm denoting G star with a hat. And then Drinfeld and Gavarini proved that the QUE admits a canonical Hopf subalgebra, so there's a kind of lattice inside it here, U prime, such that when you specialize that subalgebra, then you get exactly the Poisson algebra of functions on this formal Poisson-Lie group. So let me give you maybe the simplest example of this. So let's start with the enveloping algebra with trivially extended coefficients, the standard product and the standard co-product. So I'm not deforming anything. I'm just putting in the H bar for the right. So then the bi-algebra that corresponds to it is G with its standard bracket and the zero co-bracket here. When I dualize that, I find G star with a zero bracket, so the abelian Lie algebra G star, but a non-trivial co-bracket. And it then follows that the Poisson-Lie group that I get is G star as a Poisson-Lie group with zero Poisson, so abelian Lie group and the KKS Poisson structure. Okay. And in this case, what is this algebra U prime introduced by Drinfeld and Gavarini? It's the subalgebra of formal powered series like this, where the coefficient of H bar to the n is of order at most equal to n. So you can think of it as a kind of completed Riesz algebra of UG with respect to its filtration. And if you think of it like that, then it's obvious. Then if you specialize to H bar is equal to 0, you're going to take a completion of the graded. The completion of the graded is a completion of S of G, and S of G is indeed the functions on this formal Poisson-Lie group. Okay, so if you like, you can revisit this theorem as saying that this is a very well-known story, and then they generalize this to, this can be generalized to an arbitrary quantized enveloping algebra and get Poisson-Lie groups which are not just flat spaces, like they're not linear, they're not vector spaces. Okay, so now that I've reminded you of this ingredient, let me now state my theorem with Xiaomeng. So in short, and then I'll flesh it out a little bit. The theorem says that the semi-classical limit of this transcendental construction of the quantum group, the one you get from the dynamical KZ equations, is exactly Boalch's construction of the dual Poisson-Lie group. Again, this is kind of more supposed to be a slogan. I'll make more precise statements in a moment. And as a corollary to that, you get another different proof of Boalch's statement that the Stokes map, the one that takes Stokes data from the differential equation, is a Poisson map. Okay, so now let me kind of flesh out a little bit the first statement. So there's a key observation, which is that the transcendental construction of the quantum group started from this irregular KZ equation here. And then Boalch's construction started from this differential equation here, which I'm calling IOED, so sort of irregular ODE. And so the first claim you can make, and I'll explain in a second, is that these differential equations, not only do they look the same, but actually there's a precise sense in which the semi-classical limit of this equation is exactly this differential equation here. Okay. So that's the claim I want to make. So let me explain it in a little bit more detail. So first of all, we're going to look at the dynamical KZ equations not as valued in UG tensor UG, but rather UG tensor U prime. So this is this subalgebra, this completed Riesz subalgebra. And we can do that because both mu1 and H bar omega lie in this Riesz subalgebra. See, H bar omega, let me remind you, H bar omega is, well, maybe actually I wrote it here. So H bar omega is here, right? So I can write it as a sum of XA, H bar, XA. So the second leg of this, it has exactly the property that the coefficient of H bar, the order is lower in the filtration. So this is the new tensor prime. So semi-classical of this will mean that we now agree that everything lies in U tensor U prime. So I can then take their image when I put H bar is equal to 0. And what do I land in? I land in UG tensor completed tensor SG hat. And I G star on G star valued in UG. Okay. All right. Now, what is the semi-classical limit of mu1? It's just mu. And what is the semi-classical limit of H omega? This is the map. It's an easy check. It's a map from G star to G that just takes the first leg, or the second leg rather, of omega. So once you've done this, you see that this proposition that I claimed, that the fact that this semi-classical limits to this, holds provided that this A is equal to mu, and that B here, which was a fixed element of G or G star, is regarded as a parameter. Because the semi-classical limit of H bar omega is exactly this B as a parameter. Okay. So now I can state the kind of our main theorem precisely. So let's take the dynamical KZ equations, and let's take its Stokes matrices. So you remember I had these two solutions, so I can analytically continue them and then get these two Stokes matrices on the one hand. And on the other, I want to compare them with the Stokes matrices of the irregular ODE. Specifically, I'm going to do a couple of massages here. I'm going to take these Stokes matrices, so forget the hat for now and forget that there's a B. So these are the Stokes matrices that Boalch was taking. I'm now going to remember, as Boalch was doing, that they are a function of this parameter B, and they're actually an analytic function of that. So I can take their Taylor series with respect to this B. And I'm now going to take their formal Taylor series. So that's what the hat is for. So now this S plus or minus hat B is the formal Taylor series of the Stokes data with respect to B, expanded at B is equal to 0. Okay. And now that I've made these two changes, what are they? They're formal functions on G star with values in the upper and lower unipotent groups. Okay, so now once we've changed the point of view a little bit, then our claim with Xiaomeng is that, first of all, the quantum Stokes matrices, they don't just lie in U tensor U, they lie in U tensor U prime. Okay. And secondly, so then I can meaningfully take their semi-classical limit. And then their semi-classical limit is exactly these Stokes matrices coming from the differential equation by Boalch, but in this after this massaging, so they're formal Taylor series. Okay. And once you proved that, then the second statement I made, which is that the Stokes map is Poisson, follows directly from this from the linearization result of Enriquez, Ettinghoff, and Marshall. And maybe I should say something here, which is that result, as I mentioned in passing, is purely formal, so gives purely sort of formal linearizations. And then you can say, well, how does that give another proof of Boalch's result, which is a global analytic linearization result? And the point is that the Stokes map here is global. And if we want to prove that it's Poisson, well, we are just, since this Poisson map is analytic, it's sufficient to prove that it's analytic in the formal neighborhood of 0. So it's sufficient to prove that the formal Taylor series of the Stokes map is Poisson. And so you only need a formal linearization result, which is exactly what they give you, together with this result that Xiaomeng and I proved. So at the end of the day, you get an honest linearization result because you're applying a formal linearization result to an honest map. The Stokes. All right. So actually, I'm done. So I guess I finished a little earlier. So thank you very much.
That's great. Thank you very much for your talk, Valerio. Does anyone have any questions?
Sure. Can you say again how this quantum wild group action, break group action of Lusztig appears here? You kind of mentioned the beginning, but the last statement.
Yes. So okay, let me say that. So how do I? So for now, it appears kind of by how to say this well. So it kind of appears. So let's see. So you have the Drinfeld category, right? And then you have this. So flavor-wise, it's a little bit like your restriction functors with Pavel, flavor-wise, which is that you have a family of fiber functors, a family of fiber functors labeled by mu in H reg. and more or less, well, not by definition, by the fact that this, then you can ask how do these fiber functors vary with respect to the parameter in the Kazhdan. Then it's this Casimir equation, right? Then I wrote. So there's a monodromy action of the braid group on this fiber functor, and this monodromy action, almost by this result here, is the monodromy of the Casimir equation. Okay. Which is not something you would be able to say, for example, with Kazhdan-Lusztig functor or any other very good functor that you handed. If it didn't, it wouldn't necessarily have this property. And so then you can kind of summarize this package of a family of fiber functors, the monodromy which is controlled by this differential equation. This is what I call a Coxeter. This is a Coxeter, a braided Coxeter structure on representations of the enveloping algebra, maybe with an H part thrown in. And then I proved that there is I proved the cohomological rigidity result that says that there is essentially only one such. And because if I take the R matrix and the quantum group, and I take the Lusztig operators here, that's also a braided Coxeter structure. Then those things have to agree. So that's how they appear. So for now, this is cohomological, but as I mentioned with Andrea, we have this ongoing project. And again, the same story is true for the symmetrizable Kazhdan-Lusztig case. With Andrea, we're actually reconstructing the quantum group inside this, but in an explicit way. And the hope is once we've done that, we should be able to prove this without invoking any cohomology whatsoever. So it should just follow from. I don't know if that answers your.
Yeah. And I don't know if I can also go back to this question about the meaning of the name dynamical. So I thought that dynamical means that there are some sort of more difference equations, and maybe you said it, but in responding to my question in the chat.
Again, I don't really know why it's called. I would imagine it's because you have a dynamical variable, and now this dynamical variable is, I mean, in a kind of case theoretic context, this Casimir equation would become a difference equation. So here we're kind of in sort of the most degenerate possible setting where you have this kind of, so to speak, quantum differential equation, but it's not a quantum differential equation. It's the Casimir equation, if you like, but it's not trigonometric, right? It's rational. And dual to it, you have the KZ equations. Does that make sense?
Yeah.
So yeah. So in K theoretically, one of the differential equations would be replaced by a difference equation. But here we're sort of lower down the generation run.
Okay, well, are there any more questions for Valerio? Well, if not, let's thank Valerio again for his very nice talk.